Now that we understand that standard deviation is that average distance away from the center, and we understand how to calculate it, we're going to look at a model that's going to utilize the standard deviation as well as the mean. So I've brought us back to this previous slide where we're actually looking at the formula because I want to go over one other thing and remind you about means and standard deviations. We said in a previous video that the mean of a data set is best used when we're describing symmetric or bell-shaped data. That's because it is easily influenced by very large or small values, and so it's not the appropriate center or measure, when we're dealing with skewed data. So we've said the mean is only for normal and symmetric data. Since the mean is a part of our standard deviation formulas, it would imply then that the standard deviation also is only going to be used on symmetric or normal shaped data. So that's going to bring us to our empirical rule. This empirical rule is for data that is only in the shape of the bell-shaped distribution, so similar to the graph that you're seeing here. And in this empirical rule, we're going to use it to be able to model where I could expect my data to fall with respect to the center and so forth. So you're going to want to copy this down and make sure that you understand this empirical rule, and we're going to take a second to explain it. Starting in the center of my graph is always going to be the mean, because that's our measure we're using for bell-shaped data. And then as I move above the mean, I'm going to move one standard deviation above the mean and keep going 2 standard deviations and 3 standard deviations. And each time I increment, the area between those values is changing. So you can see here I've highlighted 34, 13.5, 2.35, 0.15 is above the 3 standard deviations. So if I wanted to talk about the data, how much of my data is falling between the mean and 1 standard deviation, that occurs at, that entails 34% of my total data. And then if I wanted to move even further out, if I wanted to talk about the data falling in between 1 and 2 standard deviations, that should be approximately 13.5% of my data, and then you can keep going. So I hope you kind of understand the way that's being written. Because this is a bell-shaped distribution and symmetric, as we move to the left of our center, we're just repeating these values. So we're going to move 1 standard deviation to the left of the mean, 2 standard deviations, 3 standard deviations, and so on. And these are the area that we would expect to contain that much data. This is the percentage of data that would be contained within each of these bars, I should say. So understand that the total area under this curve is supposed to add up to be 100%. So everything under this curve should be 100%. And now if I want to get specific and say, I'm only interested in how much of my data is going to fall within 1 standard deviation of the mean. So if I start here at the center and I move to the left, that would be 34%. If I move to the right 1 standard deviation, that's another 34%, and that totals 68%. So 68% of the data that I'm looking at should fall within 1 standard deviation of the mean. Let's go even further. Let's talk about maybe 2 standard deviations away from the mean. So now I'm at the center. If I move all the way out here 2 standard deviations away from the mean, that's going to entail 13.5 plus 34 plus 34 plus another 13.5%. So I can expect 95% of my data to fall within 2 standard deviations of the center. And then you can keep going here. You can see that we have 99.7% of my data is falling within 3 standard deviations of the mean. And that just leaves a very small percentage falling outside of that, right? That only leaves what, 0.3% left of the data to be outside of 3 standard deviations away from the center. The idea behind this is it's a way for us to kind of be able to look at where we can expect the data to fall, and then what happens if it doesn't fall within that range that we are interested in. Let's go back and talk about the 95 percentile. So we've said that 95% of my data is supposed to fall within 2 standard deviations of the center. So if I can expect 95% to fall within 2 standard deviations, 5% of the data, because that's what's left over, to make 100, 5% of the data is going to fall outside of that. So when I have data that falls within this 5% zone that I'm kind of highlighting over here, that's where we can kind of say, maybe I need to look at those values. Why did they not fall within? I'm expecting 95% of my stuff to fall within 2 standard deviations. And so if it falls outside of those 2 standard deviations, I need to look at the data again. I need to try to figure out why it happened. It just makes me kind of look at it and ask why and maybe investigate it a little bit further. So this is what the empirical rule can help us determine when we're looking at individual data sets. Let's look at an example that applies this empirical rule. In this example, we're going to take a previous example we've seen already to be able to determine and estimate where certain data is going to fall using the empirical rule. In order to apply the empirical rule, we first have to determine not only the mean, but the sample standard deviation for my data set. So we've seen this in our lessons over mean, median, and mode. This is an example where BYU students collected data on the speed of vehicles traveling through a construction zone where the speed was posted, and they sampled 14 vehicle speeds, which you see here. I'm going to put those values into StatCrunch, and I'm going to determine not only the mean, but the standard deviation. So when we come over here to StatCrunch, you'll see the column that I have here for speed. Now, we want to calculate the standard deviation as well as the mean, so I'm going to select the speed column. We're looking at sample means and sample standard deviations, so I need both of those values there. I'm going to hit compute, which you can't see. And here are the mean and standard deviation for the data set. So we're going to say the mean is 32 and the standard deviation is 6. But let's check one more time to make sure that I can apply the empirical rule, because we can only do that to data sets that are bell-shaped or normally distributed. So we can quickly verify that by going to histogram, choose speed, and then I'll hit compute. And you can see that the shape of this histogram is a bell-shaped distribution, so we're good to go on applying our empirical rule. So we're going to use a mean of 32 and a standard deviation of 6 to apply the rule. So to use the empirical rule, we're going to create a number line specific to this data set. So I'm going to draw a number line here on the screen. And in the middle of that number line, I'm going to write 32 because that's the mean of this data set. Let's go above the mean. So I'm going to come over here and I'm going to add one standard deviation, which is 6, to 32. So 32 plus 6 is 38. So plus 1 standard deviation. Now let's add 6 more to 38 and we should be at 44, which is 2 standard deviations above 32. Let's add 6 more to 40. We are at 50. That's 3 standard deviations above the mean. And we're going to go in the same, we're going to do the same thing going in the opposite direction. So 32 minus 6, which is going to give us 26. which is minus 1 standard deviation. 26 minus 6 is 20, or minus 2 standard deviations. 20 minus 6 is 14, or minus 3 standard deviations. So that's how I calculate the numbers on this number line. You start in the middle with your mean, and each time I'm going to add, if I go above the mean, I'm going to add my standard deviation to each of these numbers as I move up the number line. And if I go in the opposite direction, if I go below the mean, I'm going to subtract my standard deviation. Let's also add to this our percentages that we can expect based on the empirical rule. So the empirical rule says way out here to the left of 3 standard deviations below the mean, that should encompass 0.15%. The next value would be 2.35%, 13.5%, 34%, and then since this is symmetric, we're going to use those same numbers going down. So 34, 13.5, 2.35, 0.15. So what I wrote in red is the percentage of data that falls within each one of these segments. So the question we want to look at is, it says use the empirical rule to estimate the percentage of speeds that fall between 26 and 38 miles per hour. So let's look at our number line again. I can find 26 here and 38 here. And so the percentage that's falling between 26 and 38 ends up being what, 68%. So 68% of the data fell within 26 and 38 miles per hour. This is the data set we're looking at. Let's look at another one. Let's say that I want to use the empirical rule to find the percentage of drivers whose speeds were 26 miles per hour or higher. So they would be exceeding the speed limit here. 26 miles per hour or higher. So here, in this case, I'm going to take my 26 again. So I have 26 here, and I want to figure out what's the percentage that goes all the way up to the end of my number line. Well, there's 2 ways to do that. I can add up 34, 34, 13.5, 2.35, and 0.15. All of those numbers add together to give me a total of 84%. So 84% is going to be above my 26 miles per hour. Another way you could have thought of this is I could have taken 100% minus what was below the 26 miles per hour, or in other words, what was left over. So that would have to be, what, 16%. So the 13.5, 2.35, and 0.15 would have to subtract from 100 to give me what was left over. Either way you see it, you either add everything up as we move in the direction above the question, or you could subtract and take what was left over to answer the question if they want that way. So this is how we would apply the empirical rule, but you have to make sure that your distribution is bell-shaped. And then we are creating a number line here that is specific to the mean and the standard deviation of our data set. So the first thing you have to do is number your number line here that we did. Number your number line with respect to the mean and the standard deviation, and then determine the percentages for the data.